Thank you, Kilian. I'm very glad to see you here on my second lecture. Thanks. And when people watch TV series, usually there is a brief summary of a previous episode. So I study functional limit theorems for perturbed random walk. So I start with just general random walk. For example, let me recall Donsker theorem. So if jumps are IID with mean zero, finite variance, and if you make proper scaling of time and space, then you will see a Brownian motion in a limit. And now we perturb transition probabilities in finite number of points and try to find the limit. And the first example that I explained 2 days ago is symmetric random walks, and we make perturbations only at 0, so make some skewness at 0. So with probability P, we go up, and with probability Q, we go down. Then it's clear that the absolute value of this perturbed random walk has the same distribution as initial random walk. And all transition probabilities can be calculated explicitly. And let me recall, okay, the transition probability of this perturbed random walk when everywhere is 1/2, and from 0 you make a step up with probability P and down with probability Q. So transition probability are this, where phi is a transition probability for symmetric. And well, you have, say, more Laplace theorem. So you have convergence of density of these transition probabilities. Well, and it is more or less clear that sequence of perturbed random walk, of scaling of perturbed random walk converges to a process, to a Markov process with the following transition probability density function. So this Markov process is called a skew Brownian motion. And let me recall you just few properties of a skew Brownian. This process was proposed by Ito and McKean in their book, and they constructed a skew Brownian motion as follows. At first, they considered a reflected Brownian motion. So these are excursions of a reflected Brownian motion. So excursion is a part of trajectory such that beginning is 0 and the end is 0 and no zeros in between. Then they enumerate all excursions in a measurable way. Okay, you have to be careful. When you hit 0, there are infinite number of excursions in the neighborhood of this point. So there is no first excursion, second excursion. And then they do the following procedure. With probability P, they selected a sign of excursion. So with probability P, sign is positive, and with probability Q, 1 minus P, they multiply this excursion by -1. So some excursions are positive, remain positive, but some become negative, and this new process is called a skew Brownian motion. Well, if you consider this perturbed random walk with probabilities P going up from 0 and Q going down, then it is obvious that you can construct this skew random walk by the same procedure as Ito McKean. Just take reflected random walk, reflected symmetric random walk, and then flip some excursions. Okay, random walk is defined only in integers instead of time, but I make this picture. From this definition, you can see that, well, this process is continuous. Absolute value of skew Brownian motion has the same distribution as absolute value of Brownian motion. Well, if gamma is 0, so gamma is p minus q. P minus q or 2p minus 1. Then, gamma is p minus q. So if gamma is 0, means p is q, is 0.5, then this q is just usual Brownian motion. And if gamma is 1, this means that p is 1, then you get reflected. Well, you can describe this process in constructive way, like Ito-Makin, by transition probability density function. You can write a generator, but you have to be careful. What is the domain? Domain is functions that are twice continuously differentiable everywhere except of 0. The second derivative is bounded, and you have some additional condition at 0. Okay. The next result is stochastic differential equation for the skew Brownian motion. This result was obtained by Harrison and Shep. And you see, increments of the skew Brownian motion behaves like increments of a usual Brownian motion everywhere except of 0. So if there is a representation, a stochastic differential equation, it should be Brownian motion plus something that may increase only when process hits 0. Okay, and the equation is this, where L is a local time of the skew Brownian motion at 0, and gamma is just this gamma. Harrison and Shep proved that if the absolute value of gamma is less than or equal to 1, then there exists a unique strong solution to this equation. And that solution to this equation is a skew Brownian motion. And if the absolute value of gamma is greater than 1, there is no solution, neither strong nor weak, so no solution at all. Okay. Sometimes this local time is written like a delta functional, and Perturbed called such type of equations like a diffusion with generalized drift. Indeed, what is the local time? The local time of this process is a limit as epsilon tends to 0, integral from 0 to t, f epsilon x of s ds, where f epsilon is this function, 1 over 2 epsilon times indicator of absolute value of x less than epsilon. This function converges in generalized term to a delta function, Dirac delta function concentrated at 0. So sometimes this equation formally can be written as in the following way: plus delta of x of s ds. Well, and I understand t dt, and I understand this like a limit of like approximation. Yes. So the statement is, it coincides. Yes, it is. Yeah. And the next interesting question is the following. Okay, let's try to approximate this process in the following way. Let's consider sequence A epsilon that approximates delta function. Well, delta functions times alpha. And try to pass to a limit. And well, what should a limit be? Okay, alpha times delta function at 0, but this is not true. And it was shown by Perturbed that the limit is a skew Brownian motion, but the parameter gamma is not alpha, but hyperbolic tangents of alpha. And this means that when you study a skew Brownian motion, you must be very, very careful, because invariance principle, we have invariance principle, but the parameter is not the same. It is different. Actually, I think that Perturbed was the first person who write equation, stochastic differential equation for the skew Brownian motion, and even in more general multidimensional situation. But his approach was from PDE theory. So he studied only weak solutions, and found some densities, semi-groups, and so on and so forth. And then he gave a rigorous meaning. What does it mean? What does it? Where the integral is divergent. Okay. Okay, let me tell you. It depends. So if I think if A is divergent and positive, then the limit is reflected Brownian motion. But if A has this structure and scaling is not this, but maybe a little bit different. So you don't divide by epsilon, but maybe epsilon times logarithm, another interesting process may appear. Well, so I call this process a Brownian motion with a hard membrane. Antoine Léger called this process snapping out Brownian motion. So we wrote papers almost at the same in 2015, but our approaches were a little bit different. And the limiting process is the following. It behaves like reflected Brownian motion before the local time of this reflected Brownian motion so reach some exponential level. Then it switch, and you have a reflected Brownian motion here. Well, it depends on this shape. And again, it reaches another exponential level, possibly with another constant, and again and again. So if A is different, then I think maybe I have infinite integral. I can't formulate the rigorous statement, but there are other possibilities. Okay, let us continue. Well, and the main problem is this. We consider integer valued random walk that behaves, whose increments are size if the random walk is here or here, and I'll call it regular behavior. And when you enter the set minus MM, I'll call this set membrane. then behavior is different. When you exit, again, increments have distribution sign, and so on and so forth. Well, it is not written but I will always assume that all states communicate. Otherwise, it is not interesting. For example, if you come here and live in membrane, this case is not interesting. And under the minimal assumptions, well, that jumps in membrane have finite expectation, the Donsker scaling limit of X is a skew Brownian motion. So this is one of the results. Later on, I will formulate a more general result when jumps above and jumps below have different distribution, maybe have different variance. They should be mean zero here and here. The interesting equation is how to calculate this parameter of permeability gamma. I will also give you a natural formula. And now a short review. So the first paper on this topic was a paper by Harrison and Shep, and there are a lot of different approaches. For example, Minlos and Zhizhina, they used generators, and they proved that generators, in some sense, generators of random walk after some scaling converge in some sense to a generator of skew Brownian motion. But you see, this is discrete object and skew Brownian motion is continuous. So this method was really hard, and it was not natural explanation what is gamma in terms of these perturbations. Well, in 2011, a little bit earlier, I posed this problem to my master and then to my PhD student Yuri Prihodko. And at first, we considered the case where jumps were plus minus one everywhere outside of membrane. And we found, we proved that the limit is skew Brownian motion. We used excursions. We used excursion theory. We cutted some parts and gluing them together and proved the result. Ngoy and Pinier, they used classical approach. They proved weak relative compactness plus convergence of finite dimensional distributions. They considered the following model. Regular behavior here, but when you cross zero, then you jump to zero, and then you exit from zero, and all exits are IID with some distribution at. Well, if you jump down, increments here may be different from there. They may have different distribution. And imagine how it is difficult to prove something using finite dimensional distributions, because you cannot write them explicitly. Well, you can write them explicitly, but not in a nice way. So you have to make some estimates. And today I will use martingale problem approach. So at first we found this with Alex Iksanov, and finally the most general result was proved by Ilya Pavlukevich from Jena University and me in 2023, and the paper was accepted 2 days ago to Alia. Today I will consider not only random walks on R, but also more general case when you have random walk on a graph. And let me mention a few works like by Increments and Kiefer and diffusions that were constructed by Wenzel and Friedlin on a graph. Well, sometimes, and the limit object will be a Walsh Brownian motion. I will tell what is this a little bit later. Or for example, diffusions in narrow tubes. So what does it mean? Assume that you have narrow tube, something like this, and you have something Brownian motion here, Brownian motion here, Brownian motion here, something in between, and then you shrink the picture, and you see just a point with three rays. And in a limit, so Wenzel and Friedlin also has some results when such diffusions converge to a Walsh Brownian motion. This paper by Alexei Kulik, in this paper, Alexei Kulik considers the following problem. Assume that you have a diffusion on a graph, with many rods. Maybe so here Brownian motion, but some rules here. For example, you go here. If you come here, then there is just door, and you can walk. For example, this curve, but never come here. So there are a lot of possibilities. And then you shrink the picture, and you have like a knot. So you have this picture, and then you make the scaling smaller, and smaller, and look, what is this? Unfortunately, this paper was never published. You can find it only in archive. Actually, Kulik used resolvent technique, and it was very efficient. Well, resolvent technique for this, I think martingale problem is better. But tomorrow you will see that resolvent technique helps a lot. In close, but in the case where tails are heavy. Okay, and there are some references for multidimensional perturbed random walk. For example, if membrane is finite and you have two-dimensional random walk, then usually the limit is just two-dimensional Brownian motion. In this paper, we considered Brownian motion in a multidimensional space where we have a membrane and with some periodic structure. For example, there are some doors that you can pass from here to there, or say some doors that come here, or two-sided doors that you can come and exit or just reflect it. And in this case, the limit process was a Brownian motion plus local time at this membrane times some direction. So it's some analog of skew Brownian motion. Well, and next, let me explain you. So everything is written, but let me make a picture. It is much better. Let me explain you what is Walsh Brownian motion. The Walsh Brownian motion is an analog of a skew Brownian motion, and let us assume that you have few rays with a common endpoint, say in 0. So this ray is number 1, number 2, number 3, number m, and you have positive numbers p1, pn. And behavior of Walsh Brownian motion is that. So it's Brownian motion on the ray until you hit 0. And then new excursion selects a new ray with case ray with probability pk. Well, you have to be careful when you say selects the new one. But well, you can write transition probability density functions, resolvents, generators, everything. I think it's easier to, yeah, and you can use Ito construction, Ito and Maki construction. You start with reflected Brownian motion, and let me say that each ray has its own color. When you're here, then the color is red. When you're here, the color of excursion is yellow. So just paint these excursions and select color number k with probability pk. So you just color this trajectory and say, well, Walsh Brownian motion is a colored reflected Brownian motion. So there is one-to-one correspondence between this and this. And sometimes I will call color like label of this. Originally, construction was just rays with common endpoint in two-dimensional space. But sometimes it's easier to work with the following picture. Assume that you have so m color, so m-dimensional space. So now three-dimensional, and take coordinate axis and independently, yes. There is no, it is not, because there is no next excursion. You see, there is, when you hit zero, there are infinite number of excursions. So you have to enumerate them in some measurable way and then color independently. So this is rigorous. Yes, yes. Yes. Oh, okay.
Yeah, because the excursion.
Yeah, if you construct this from E to E.
Not any others. And you don't have to have finite. You can have.
Exactly. Yes. Yeah, but today I consider only finite number of marks. But yes, you're absolutely right that you can use infinitely number of marks. Yeah, yes, this is possible.
I guess if discrete Markov chain type thing, you would see the stationary distribution of the Markov chain. Because if you were doing a discrete model,
for discrete, yes. For discrete, yes. Yeah, it is possible, yes, but we have to be careful when we are doing this. Yes, and okay, and now one more construction, because you see, I want to have a process, and the process of marks is discontinuous. It's very terrible, as we discussed, because when the red mark is over, then there are too many white, yellow, other marks. So I would like to work with continuous processes. And when we work here, we work with continuous. And I will say, okay, what is the Walsh Brownian motion? So let me say that it is a process that lives on coordinate axis. And what does it mean? For example, if you are here, then all other coordinates are 0. So the process is, well, d-dimensional process such that only one of the coordinates may be non-zero. Okay, and it's strong Markov and behaves like Brownian motion before before the hitting 0. And well, I cannot make three-dimensional picture, unfortunately. Well, yeah, unfortunately. So let me make, instead of one three-dimensional, three one-dimensional pictures. So this is time. This is space. And okay, assume that the first excursion is white. Then the red coordinate is 0, yellow coordinate is 0. So, okay, three one-dimensional. So picture number 1, picture number 2, picture number 3. So if excursion is positive here, then here 2 are zeros. Well, assume that then you're here, then these two parts are 0. And well, again, white, then maybe red, and so on and so forth. So yes, they are positive. Yes, they are positive.
Semi-axis.
Yes, this is semi-axis. No, it's semi-axis. It's semi-axis because Walsh Brownian motion is this. You see, is this? It's non-negative, but it lives on rays. It doesn't take negative values. Yes, yes, I can. Yes, when I consider skew Brownian motion, I should make like this, but then say, well, I don't want to. I have a color. I have a color and position. So I know that red means negative. So I can write red positive, meaning that direction is negative.
No. That would make
you mean that I can consider axis? Yes, but then you obtain again Walsh Brownian motion. Walsh Brownian motion exactly with doubled number of rays. Yeah, so if I take these three pictures and put it into space, then you'll see trajectory of Walsh Brownian motion. Well, it would be nice to have some wire and then to take and then show you space. Oops, Walsh Brownian motion in space. Okay, and what happens? Okay, and now the next property of the Walsh Brownian motion that follows from the definition. Assume that you have some set of indices, and let's consider this process. So some colors. So you sum some colors and say they're positive, and some other colors and say they're negative, multiplied by -1. And then you will see just a skew Brownian motion. So if I prove some limit theorem where the limiting process is Walsh, then I can prove functional limit theorem where the limiting process is a skew Brownian. And now let me explain you the model, and it would be better to make a picture. I have a pair. The first coordinate I call radius, and second label, like color. So the second coordinate is a color. And I assume that if the color is yellow, then the jumps, are independent, identical, distributed random variables. Okay, this is a state space, so it jumps here. I don't make a picture of time, so this is space. This is space. Forget about this. So you jump, but when you, at the moment of overshoot, you have to decide what to do. So you overshoot, and then you can change color with certain probability that depends on this point. That depends on this point and depends on overshoot. Then you can change color. For example, this is 0. You jump here, and again, you have independent jumps, mean zero, finite variance, but distribution of yellow jumps and red may be different. You are here, overshoot, maybe you return to yellow, overshoot, maybe you return to white, and so on and so forth. So assumptions, ID jumps here, ID jumps here, ID jumps here. Distributions may be different, mean 0, finite variance. When you overshoot 0, then immediately you jump to the positive side. All states are connected to avoid trivial cases, and one more assumption. This one. This means that if the overshoot is here and this point is x, then when you enter positive side, then the expectation of this random variable is finite, and is bounded by x, well, absolute value of x plus 1 times some constant which may be big. And that's all. And I'm, pardon? Yes, exactly. Then no problem. Yeah, but it may be it may be different. And I'm going to prove that Donsker scaling limit of this is a Walsh Brownian motion. But now let us discuss what are the methods. What, say, resolvents, generators, martingale problem, finite dimensional distributions. And if you think that, well, I don't want to calculate, it would be difficult to calculate finite dimensional distributions or to write generators. Well, if jumps are bounded from above, maybe resolvent technique is helpful. But theoretically, jumps are unbounded, and this overshoot may be arbitrary. So we decided to apply martingale problem, and the martingale characterization of Walsh Brownian motion is the following. The process X and the process nu are a Walsh Brownian motion, and nu is its local time, if and only if the following conditions are satisfied. Well, xi are non-negative. Well, it's clear from the definition. Only one coordinate may be non-zero. Yes. Nu is non-decreasing, and nu may increase only when x is in 0, and nu does not increase where x is outside of 0, like a local time. And the following processes are martingale. So xi minus p, that probabilities times the local time, are continuous martingales and their characteristic is this. Well, and the process spent 0 time at 0. And well, this condition was not written in original paper Barlow-Pittman-Yor, but it seems to me that you have to add it. Otherwise, 0 is a solution to this problem. Okay, and now let me explain how we can see martingale and a local time from my assumptions. And let me make a picture. Well, instead of making a picture of 3 processes, I just make a picture of 1, but with different colors. Assume that the first color is yellow, then you overshoot. Then assume that you select red. Okay. Again, then next is also red, then say white. Okay, let me you add here random variables that are independent and have mean 0, variance, finite variance. Well, assume for simplicity that variance are equal. If you shift this picture and place this point to this, what do you see? You will see a martingale. So sums of random variables that mean 0 plus, so all these increments have mean 0 and same variance. So our process is a sum of this plus this part, plus this part, plus this part. And this will be increasing process that looks like a local time, and to formulate the result and to find that probabilities, I need to introduce some exit and entrance random walks. So I will call these points exits, and these points entrance. And let's consider our Markov chain only at this point, this point, this at the exit moments. So I will call this is exit Markov chain, embedded exit Markov chain, and this is entrance Markov chain. And these Markov chains are ergodic. And okay, there are a lot of specialists in this room who studied entrance and exit random walks. And we make a reference to a paper of Ladislav Vysotsky, and some statements are just from his paper in SPA in 2015. And so we didn't know how to work with it, but after we read Ladislav's paper, everything become clear. So the first statement, these Markov chains are ergodic, and the argument is the following: with positive probability, for any starting point, you hit 0. You hit 0. So 0 is renewal moment. So this is renewal epoch. So if you have a renewal epoch, then you have stationary distribution. So stationary distribution for exits exist. And what is entrance? Just one step after exit. So again, stationary distribution. No, it was my assumption. So that we enter positive side immediately after the exit.
But where? What's below?
Arbitrary.
So it's
Arbitrarily.
it's a part-
It's a part of a chain. Yeah, but if exits have stationary distributions, then entrance also has independent. Well, for any entrance, but I need more. I need more that exit and entrance distribution have a finite moment. They have a finite moment, and another. And to prove this, we use the following statement that for any alpha greater than 0, alpha may be very, very small. There is some constant, well, k that may be large, such that for any x, for any starting point x, the expectation of the overshoot is bounded from above by this. So this statement was known, but it was very clearly formulated in Ladislav's paper. And you have this, and what was our assumption? Yes.
chain. Have a joint.
Yes.
So why don't you consider the pair of chain?
For the result, we do not need it. To prove the theorem, we don't need this. But if you wish to discuss this pair, maybe you have to ask Vladislav or Alex. Okay, and now let me formulate the result. So, well, for simplicity, I assume, okay, the result is this. The radius, the color, and we consider this vector, and we divide by square root of n, and we also divide by square root of variance, and the limit is Walsh Brownian motion, and the question is, what is probabilities? And the answer is this. And the answer is this. You have to take entrance random walk, exit random walk, and pk is difference entrance minus exit, expectation of entrance minus exit, times indicator that the label is k, and divided by the same thing, but without the indicator. And that's all. So very, very natural formula. Well, and you know what is entrance, what is exit. There is a relation between them. So you can write in terms of entrance and exit, but also entrances, but also exits. So it's up to you. R0. So R0 means the following. So entrance. So R0 is positive. So you have a stationary distribution on the positive numbers. So you take R0 with you have a distribution. You have a distribution. R0 for, I mean, if you start from this entrance stationary distribution, R0 in stationary distribution. Yeah, P entrance or P exit here. Yes, R0 and L0 have this entrance or exit distribution. So you have to average with respect to stationary distribution of entrance or exit or both random walks.
So again, R0
By entrance, yes. Yes, yeah. Distribution of, in this formula, distribution of I0 is pi entrance. And distribution of R0 here is pi exit. Yeah, yeah. this and this, they have different distributions. Stationary distribution of entrance or exit. So sometimes we can calculate, and I'll show maybe some examples. Well, and what is the way of proof? Well, I showed you martingale, and if we delete colors, then the limit will be reflected Brownian motion. And here we used my previous result, my previous talk. Because you see, you have random walk that can overjump. It has some reflection. It's like mode 1, mode 2. We use some large numbers for Markov chains, for Markov chains that have stationary distribution, and the stationary distribution has a finite moment. So it was important. Yes, and the first step was to prove that this picture without colors converges to reflected Brownian motion. So then this sum of jumps from here to there converges to a local time. So we get this process nu. So we know what is this. And then, okay, if you sum only yellows, and if you don't add yellows, but add yellows when they appear, you have a martingale again. Sum of reds is a martingale. So you have d martingales. And the only thing is to show that if you subtract something like this, it is the martingale again, and well, it can be done. It is not so difficult. Well, it is a technical thing how to calculate the characteristic, but for prelimit, in this prelimit case, characteristic is, for example, for red, 0, then just time when you spend in red mode, maybe divided or multiplied by square root of variance, and then 0 again. So, well, it is natural. And then, okay, some calculations, weak relative compactness, but it is not so difficult. And what is the result for skew Brownian motion? Again, you have to introduce some entrance and exit random walks. Let me just explain you. So you have a membrane. And I will say that here, it is the red line. Here, it is yellow color. And when you overshoot this level from the right, you virtually enter the membrane. So this is like membrane for red. And when you overshoot from here to here, it's like membrane for yellow. Well, my assumption was you immediately exit membrane. For example, if you are here, you can make a lot of jumps before you exit, but they are of order square root of n. So the number of them is small if you compare with n. So it is not really effect. And another difficulty, when you jump from here to this, I say, well, in some sense, you enter to the here, yes, but from another point of view, you immediately select yellow color. So what does it mean? This means that, okay, let us formally add one step. Like you jump here, and then you jump here. And the number of overshoots is also like square root of n, so it's all small of n. And we apply the result, and we also get a formula for skewness in terms of some entrance Markov chain. Probably I don't have time. So thank you for your attention. Yes.
And then
Mm-hmm.
number of being zero.
Yes.
And then known in the classical situation.
Yes, exactly. It converges to a local time times constant. Exactly. You. Yes. Yes. Actually, we do exactly. So at first we have convergence of pair of X, and this overshoots. But also, you are absolutely right. When you consider visits to zero, it converges to a local time. So to a local time times, and it's very easy to understand what is this, because let me tell you, you have these entrance and exit Markov chains, and well, if you have membranes, a membrane, you have many visits, but these exits and exits, it's like renewing epochs. And you have renewing epoch, and then you have some additive functional. It behaves, it depends only on this. For example, number of visits to zero. And if you have some Markov chain, and if you, for example, if Xn is a Markov chain and exit or exit entrance, and if you if epsilon k are ID and independent of this Markov chain, then you have a law of large number for this, for this. And this epsilon k it may be, so it is some functional. Well, it is some functional of exits maybe and entrances. So it is possible. So I didn't make it for number of visits to zero, but I counted, say, number of crossings, and some classical result can be obtained, or some crossings times size of crossing. For example, crossing from above, crossing from below, something like this. But you're absolutely right that such functionals like a number of visits to zero, or number to visits to zero plus 2 times number of visits to 1, yes, it converges to local time times something. Yes, yes. Yeah, if you can visit zero with, okay, if zero communicates with states outside of membrane, then the limit is the local time times a constant. And I think you can write the constant in terms of exit or entrance distribution. Finite variance. Okay. Yes.
So you imagine taking alpha 312 and
I will tell you this story tomorrow. So tomorrow my talk is about the case when you have alpha stable everywhere outside of singular point, where you also have another alpha stable at this singular point. Yes. Mm-hmm. Mm-hmm. Are not like. Yes. Yes. So tomorrow I will tell. Yes. So next talk is on this topic. And it is very difficult to explain what is the limit.